Welcome back to another series of econometric discussion. We have talked about linear systems of equation, linearities in mean and variance. Well, we're talking about var and structural var. Today we're going to start talking about non-linearities in mean or in non-linear systems of equation. Now, why is it important? Because many very important methods and processes have been suggested by non-linear systems of equations, such as artificial neural networks, which is believed to be the base for many intelligent programs that have been created very recently, and Markov switch model, a very important and a very heavily studied method in understanding crisis impact in different periods of time in the last decade. So we're gonna start talking about them, whereas our structural models are able to capture many of the characteristics observed in time series data, such as randomness, cycles, and stochastic trends, as we have seen. These models come up short in capturing, where we're talking about linear systems of equations and linear models here. These models come up short, however, in capturing more extreme events such as jumps and asymmetric adjustments across cycles that cannot be captured adequately by a linear representation. This chapter deals with models in which the linear mean specification is augmented by the inclusion of linear terms, non-linear terms, so that the conditional mean becomes non-linear in the lagged dependent variables and lagged residuals or disturbances. So now we are going to convert our linear models to non-linear ones, especially in the lag dependence and lag residuals. Examples of non-linear models are threshold time series models or TAR models, such as threshold autoregressive models, artificial neural networks, bilinear models, and Markov switching models. Non-parametric methods are also investigated, where a parametric specification of the nonlinearity is not imposed on the structure of the model. We'll talk about non-parametric methods further when we talk about Garch and mGarch. Basically, nonlinearities in variance are applied in Garch models. And then in chapter 21, nonlinearities from the specification is discussed. So, what first motivating example? Earlier in var, we have studied linear time series models, where those chapter yields solutions that are characterized by convergence to a single equilibrium point. Our data used to converge to a single equilibrium point with a trajectory path exhibiting either monotonic or oscillatory behavior. By oscillatory, I mean the lines are going up and below positive, zeros, which is sometimes positive and negative, or magnification and dampening effects. So an AR2 model, consider a linear AR2 model, as we are familiar with, is phi1 yt minus 1 minus phi2 yt minus 2 with the mu. This is the AR2 model mapped, where y0 is 0.5. This figure shows that the dynamics exhibit damped oscillatory behavior, which dampened over time, starting from initial value y0 equals 0.5 and converging to an equilibrium point, which is y equals y0 divided by the equation, basically in converging in the equilibrium point, where y equals y0 divided by the autoregressive equation, that is the convergence point, right? 0.7 plus 0.6, which equals 1, right? So our initial point was 0.9, our constant was 0.9, and the other values, the autoregressive parameter coefficients are 0.7 and 0.6. So numerator we have our constant, and in denominator we have basically taking everything on the left hand side except for the constant or the mean actually. So this equals what the mean is, 1 minus 0.7 minus plus 0.6. so y minus taking the equations rest of the part on the left hand side, then taking the coefficients. So this is the equilibrium point or mean value, which is 1. The phase diagram in panel B shows how the process spirals. So the whole process is spiraling towards this equilibrium value, or basically which we know as the mean reversion, right? So mean is here, you take the stuff left hand side and then you just solve for the mean, taking everything below mean, and you have the mean reversion here. While the linear class of models can capture a wide range of patterns commonly observed in time series data, there are some empirical characteristics that these models cannot explain. Examples of this nonlinear behavior are limit cycles, strange attractors, multiple equilibria, and asymmetries. Okay, and these what results us to talk about nonlinear equations. So I have learned something very important and very interesting, that when we are talking about autoregressive models, when they are stationary, we basically see a mean reversion, and when we are talking about mean reversion, we can basically prove that ultimately our model converges to 1 simply by dividing the constant with the rest of the coefficients in the equation, in the autoregressive equation. So let's start with limit cycles. Consider the following model proposed by Tong, where y is governed by separate autoregressive process. So there are two different autoregressive processes that depends on whether it is above a threshold point, so whether or below the threshold point of 3.05. so whether your lags are above or a threshold point, you have one model. If your lag is below a threshold point, there is a different model. Okay, so interesting. Now this figure, the next one actually figures this model. And how do we explain this figure? This figure shows that the process converges to a 9-period cycle. Indeed, converges to a 9-period cycle. The phase diagram in the second panel illustrates how the process eventually settles down into a cycle. All the processes do that, known as a limit cycle. So all the processes are expected to settle down in one cycle, and that is the limit cycle, the final cycle, right? This behavior contrasts with the pattern observed for the linear time series models before, but the limit of the process is a single point. Beautiful. So this is a limit cycle suggested by Tong, who suggests that if we have threshold points and two different autoregressive parameters, ultimately they would the model would converge to a single cycle, which is a limit cycle. Settle down, eventually the equations will settle down or converge to a single cycle. Strange attractors. Strange attractors are regions where now we are talking about regions to which a process would converge, not a cycle. But once in the region, the process, once in that settling region, the process would exhibit aperiodic behavior. So they will not be seasonal, they will be probably non-seasonal, commonly known as chaos. Or inside the region, the process would become chaotic. This behavior contrasts with the limit cycle depicted previously, and in the limit cycle the process settles upon the outer parameter of the region. See, reaching here the process settles on the outer parameter in a limit cycle. An example of a strange attractor. In a strange attractor, this process will become chaotic. Is the nonlinear business cycle model Caldor, given by Caldor. So there are in the nonlinear business cycle model we have multiple equations. First, the lag difference is 20 IT minus ST, which is the output. So Y is output, K is capital, I is investment, and S is saving. So the lag difference of output is 20 I minus S, which is the output equation. Then we have the capital equation. Capital difference is investment minus 0.05 capital. Then we have investment equation, which is 20 multiplied to 2 to the power minus 0.01 YT plus 0.00001 minus square again plus 0.05 output 280 divided by capital to the power 4.5. So it's not 2 to the power minus, you can say it's 1 by 2 to the power this, and this equation is also an inverse equation squared, and savings is 0.21 YT. Okay, so dynamic properties of this model are given in figure 19.3. So this is the model representation, and as we can see, we have output against capital, output against backward propagation, output forwarded, then capital against, well, again capital in the next period, and then time against output. And how do we explain this? Figure 19.3 highlights the strange attraction properties of the model with regions of attraction characterized by aperiodic behavior. So we are trying to prove that in the particular regions the model is converging, and inside the regions the model are becoming chaotic, and that is what is the basis of strange attractors. Panel D of figure, the last panel, demonstrates the sensitive dependence to initial conditions property of chaotic attractors, whereby the time paths of two processes with very similar initial conditions eventually diverge and follow completely different time trajectories. So at the end, what we are trying to say, no matter how chaotic the systems are, if they're based on similar initial conditions, at the end, well, those cycles should converge and probably follow, but at a different, follow each other at different times. That's all. So another example, the last example is multiple equilibria. The stationary linear time series model exhibits a unique equilibrium. However, more than one equilibrium arises in many situations in economics. The nonlinear business cycle model of Caldor that we just presented provides an example of an equilibrium region, right? Inside the region, the model might become chaotic, unlike the one we talked before, limit cycle, referred to as a strange attractor, where the process never remains at any single point because of chaotic behavior. So there is no equilibrium point. We cannot derive an equilibrium point 1 that we did for the previous, the very first example. As another example of multiple equilibria, consider the nonlinear error correction model of the logarithm of real money. So this is the error correction model of the logarithm of real money, which is a simplification of the model in Erickson, Henry and Prestige in page 296. So maybe we're just saying that this is a simplified model. No page, I'm not sure where the 296 page is. Okay. Okay, so this is a simplification of some model suggested in this paper where we have the error correction model, which is nonlinear, located here. So, and our omega t is IID with 0 mean and 0.005 squared variance, 0.005 variance. Now, as we know, this is the change in money, and m squared is also equals mt minus 2 plus 2mt minus 3 plus mt minus 4. This is the equation for squared mt minus 2. The nonlinearity is given by the error correction term here, mt minus 1 minus 0.1 m square t minus 1, which is a cubic with it has 3 roots, indeed 1 and squared, 1 at 0.1 stable, 2 at 0.0. So this one is stable and the rest 2 which are 0.0s, so 1 and squared are points of inflection. Just remember that for now. There are 3 cubes, so 1 is at 0.1 which is stable and the rest are in point of inflection. Simulating this model for a sample size of 500,000 that we might do generates the histogram given in the next plot. It generates a histogram, and what does the histogram suggest? The manifestation of a nonlinear stochastic model with multiple equilibria is a multimodal distribution with the majority, so it's a multi-modal distribution with a majority of the mass around the stable equilibria and a smaller mass around the inflection point. Interesting, isn't it? So it's a multimodal representation where majority of the mass is here and very less is located here in zeros, near zeros. So stable point has the stable point which represents the error correction terms nonlinearity, which represents nonlinearity. In case of a multi-model, majority of the distribution will be concentrated around that nonlinear value. Then comes asymmetries. A property of linearity is that positive and negative shocks have the same effect on the absolute value of y. Beautiful, right? So whether we are talking about dampening or inflating points, they will have the same effect of shocks on y, so that the positive shock that follows a negative shock of equal magnitude would return to the process to its original position. So beautiful oscillatory behavior, magnification followed by a dampening, or dampening followed by a magnification would finally lead to the system returning to its earlier position, mean reversion. This degree of symmetry is not always evident in the data. That is an expected symmetry. An example where adjustment is asymmetric arises in the analysis of business cycles, where strong empirical evidence exists that the duration of expansion is longer on average than the duration of contraction. So in business cycle studies like the one suggested by Harding and Pagan in 2002, there is strong empirical evidence that the duration of magnification is sometimes longer than the duration of dampening. So not necessarily the positive and negative impact will have same results, and there will be different outcome if we take the differences. So this table 19.1 gives the business cycle turning points for United States monthly data. So magnification, dampening, magnification, dampening, but however they're not equal in size. So we expect equality in linear systems of equation, but probably not in the nonlinear systems of equation, right? And that is a property of linearity, okay, or symmetric distribution. In symmetric distribution, your magnification and dampening will at the end have mean reversion, and they will have equal level of magnification and dampening. But generally that doesn't happen. Generally we can expect different sizes of magnification and dampening, and that's where nonlinearity comes into play. The average duration of contractions is about 10 months compared to 57 months of expansions. This shows the monthly unemployment rate. So this is a Pagan's suggestion. The figure shows the monthly unemployment rate from 1947 to 2010, which reveals the asymmetric behavior of the business cycles. Large sharp upward movement in unemployment are followed by slow downward drips. So contraction, the unemployment increases, and then downward drips or expansion. Okay, we have slower reduction in unemployment. This suggests that separate time series models might be needed to capture differences in the expansion and contraction phases of the business cycle. So you might go back to the beautiful splitting up of equation, or the regional the regional thing, not the strange attractor, sorry, the limit cycle type of representation from that. Okay, even strange attractors can be a reference point. So next is this turning point, duration of expansion and contraction changing. Next come threshold models, or now we are gonna start with threshold autoregressive or TAR models. Specification: threshold time series models assume that the dependent variable is governed by more than a single regime at any point in time. Okay, so the dependent variable is governed by more than a single regime, not one regime. In the case of two regimes where each submodel has an autoregressive process, the model is expressed as yt equals lag of yt plus vt, 0 mean, sigma square variance, the structural residual, or the omega. So in which this part, the lag of yt is the conditional model given by phi naught plus I equals 1 to up to autoregressive terms phi I yt minus I with probability of 1 minus omega t and then alpha naught plus I equals 1 to alpha I yt minus I with probability of omega t. So we have 1 minus omega t probability and omega t. So yt is being governed. So this is split into two equations. This is kind of like the limit cycle model, right? When you have two logics here. So in the case of two regimes, each model has a autoregressive process. So this is the TAR model, and so you have the model divided into different autoregressive process. The variable omega t represents a time varying weighting function. So it is a time varying weighting function with the property that lies within 0 to omega. Okay, so with probability omega, this is your equation. With the rest of the probability, this is your equation that combines into this equation. So it has different regimes. It has different regimes, just like the 4 equation chaotic theory we were talking about. Okay, so what was the name of the chaotic theory? One more time. In the mean, it is good to revise again and again. Oh, we call it strange attractors. Strange attractors. So kind of like strange attractors, but with different logics. Only two different logics, which in general is specified to be a function of lagged values of yt and a set of explanatory variables x. For values of omega t close to 0, which gives you unity in terms of, you know, it's close to 0 means unity in terms of stationarity. The conditional Conditional mean of y is dominated by the first regime. Combining equations, both equations, the model can be written as, so for 1 minus omega t the first equation, then for omega t the second equation, and you have the residual vt, or we can write as take the brackets out, this is 1, then omega t is common in both scenario, so we have minus omega phi naught minus this plus this term, so minus this term plus this term, we can write them as beta naught, which is, as you can see, minus alpha naught minus phi naught and alpha I minus phi, so 1, so plus omega t and minus omega t, giving you this beta naught and beta I, alpha I minus phi I, plus structural residual forms the basis of the class. This is the basis of the class of the TAR models, which in turn nests a number of well-known nonlinear time series models. So you have nested nonlinear time series models here. Quite beautiful and quite simple, right? The key distinguishing feature of the nonlinear class of time series models in this equation is the way the weighting function is specified. So very important how we are gonna specify the omega weighting function, which is a vector, as you have seen, right? And it changes its value set of so we have different values when it's close to 0, or when omega t gets close to 0. Those is kind of like clustering the data. When your omega has different values and it is close to 0 or unity or stationary, it is governed in the first equation, and rest goes into the second equation. Beautiful, isn't it? So how omega is gonna, so we get a lot of things. We get nonlinearity, we get clustering, and we get different regions getting close to the discussion of well, strange attractors and limit cycles. So four popular choices of the TAR function or threshold autoregressive function are S star, which is smooth transition autoregressive model, where omega t's equation is 1 minus 1 by root over twice phi, and then minus infinity to integration, we take an integration minus infinity to I guess this is gamma or lambda. I always keep forgetting this is, okay, I'm really sorry, that is gamma yt minus d minus c, and then exponential. Then logistic smooth transition, where we take one on numerator and denominator, we take this part down, okay, this part down under the exponential function, okay, so gamma yt minus d minus c. So this yt minus d minus c seems very important for us, right? Because this term goes down, giving us logistic smooth transition or transitional autoregressive model. Then the self-exciting SETAR, self-exciting threshold autoregressive model, is if this term yt minus is greater than the next term c, then our omegas are unity, close to 1, and if yt minus d is less than 0, is less than c, which is the first term is less than the next term, we have omega to be 0, close to 0. And then exponential smoothing, so we have smooth transition star, smooth transition tar, we have logistic smooth tar, we have self-exciting setar, and we have exponential smooth tar, which is again 1 minus, well, the numerator. Now just concentrate the numerator out, 1 minus exponential of the whole elements in the numerator, that is squared. Here we are talking about nonlinear time series data, and up until now we have discussed that there is an important property in linear that differentiates between a linear and nonlinear time series nonlinear systems of equations. Primarily, a property of a linear system of equation is after if you're looking into the oscillations, after an equal amount of magnification, or after an equal amount of dampening, similar amount of magnification is expected in terms of a linear system of equation, which in real life in most cases is not achievable. In contrast, if we are to look at equity markets and exchange rates, we'll see that the size in the dampening and the magnifications are often different. For example, if there is a negative shock that takes 2 periods before it moves back to the mean, or it shows mean reversion, there is a positive shock that follows for another 8 or 9 periods before it shows mean reversion. Hence, it is this kind of system is necessary to be explained with a nonlinear property. Well, moreover, we need to split this kind of equations into two or more autoregressive equations. We have talked about attractors, special attractors, and then we also have talked previously about other systems of equations that are split into more than multiple equilibria. So basically now we are referring to asymmetric. So we talked about strange attractors, and also we talked about limit cycles. And in when we talked about multiple equilibria, we have seen that the autoregressive parameters are now referring to the asymmetries of the models. And then we moved on to talk about specifications. So how can we specify this kind of models? We call them, first of all, we start talking about TAR models or threshold models, which assumes that the dependent variable is governed by more than one single regime at any point in time. So when there are two regimes, we have where the autoregressive process has submodels, two submodels, which are split in terms of probability. So one has a probability of omega t, while the other one has probability of 1 minus omega t. And omega t actually represents the weighting function with that lies within, is a uniform distribution. It lies within 0 to 1. And if it is close to 0, then well, yt is the mean of the dependent variable is dominated by the first regime, otherwise is dominated by the second regime. And we have seen the equation can be rewritten as this. So that forms the basis of threshold models. And because it's a nonlinear class of models, where the threshold models are explained with star, L star, well, smooth transition autoregressive model, then logistic smooth transition autoregressive model, or L star, then CETAR, the self-exciting threshold autoregressive model. You might be thinking, why CETAR, not CETAR? Well, CETAR is a musical device in India. It's quite interesting to find some reference in a mathematics that matches to an Indian musical instrument. Ester and the exponential smooth transition autoregressive model. So these properties are basically shown, are displayed in the next figure. and there we have star, L star, set R, and S star. And in all the cases we have seen there is one common factor, which is yt minus d to the power minus c, and that changes hands basically. First in star, well, it is for a loop function, it defines the range. In L star we see that moves into denominator. In setter is just defining a binary binary specification. Well, in S star again we see the exponential function is in play. So the four models in the figure we have just sneaked quickly took a sneak peek on the properties of omega t in this figure for the four models with gamma equals 1, c equals 0, and d equals 1. The parameter d controls the delay, so yt minus d to the power minus c. So let's see what is defined by that. The parameter d controls the delay in moving between regimes. So from time we are removing the delay in moving between regimes. The parameter c represents the threshold where the switching occurs, and the parameter the parameter gamma determines the speed of adjustment in switching between regimes. So how quickly adjustment happen between regimes, the delay it takes from the time, and c is the threshold. At gamma equals 0, there is no switching with the star, L star, and S star model. So there is no switching here in star, L star, and well, when gamma equals 0 in that case, and S star model wherever we have the gamma element, reducing to the linear model, so it becomes a linear model when there is no switching. For gamma is greater than 0, beautiful, for gamma is greater than 0, there is smooth adjustment between the two regimes for star, L star, and S star model. And as gamma so we are talking about smooth adjustment, and as gamma tends to infinity, there is infinitely fast switching between these regimes with the star, L star models, reducing to the setter model. Wow, so when gamma tends to infinity, then star and L star model shows very quick switching, which ultimately converges to the setter model. So switching occurs from regime 1 to regime 2. So basically this is also shown in here. As we can see, when gamma equals 0, we have basically a linear model. When gamma equals less, gamma is greater than 0. Have we mentioned less than 0? No. If when gamma equals greater than 0, we see smooth adjustment. We see a smooth adjustment. So we see smooth adjustment happening over here. And when gamma is greater than and when gamma is infinite, is in gamma goes up to infinity, then we see a convergence of all the models to L star and star models to setter model. Here in convergence happens. So whenever a smooth adjustment is happening, that ultimately shows a convergence. reducing to star models. Well, the star model approaches the linear model again, isn't it? So a star model approaches it approaches to the linear model again. It becomes the linear model. For the star, L star and star models, switching occurs from regime 1 to regime 2 since yt minus d increases from values less than c to values greater than c. Okay, so because we have two different regimes here, for one c values are less than c, other one is for threshold, less than threshold values and greater than threshold values. So from regime 1 to regime 2 the switch happens. In the case of the star models, the dynamics of yt are governed. This is very important to remember because this actually establishes the base for Markov switch models. For example, if we have crisis and non-crisis data, we want to see when the regime switch happens with the threshold, and we want to plot that. So this is important. The dynamics of yt are governed by regime 1 for values for yt minus d near c equals 0. So from regime 1 ultimately everything is converging to regime 2. So this is, if this is up to regime 1, so, and by a weighted average of the two regimes for high and low values of yt minus d. So the last line is the dynamics of yt are governed by regime 1 for values yt minus d near c equals 0, and by weighted average of the two regimes for high and low values of yt minus d. Okay, so now estimation. Threshold models can be estimated by maximum likelihood using standard iterative algorithm, as we have always done, assuming a normal distribution term vt. Well, if w is omega t, in this case the v sign represents nu. Okay, so no, sorry, epsilon. So in equation with weighting function omega t, 1 by root over 2 by sigma square exponential of epsilon square divided by 2 sigma square, where x is equal to max p, not q. Here we are talking about a regressive parameter. D is the delay, so rho and delay for a sample of t equals 1 to t observations. So q was moving average parameter, we are estimating the delay parameter. The conditional log likelihood function from other chapters for the case of known delay parameter d is same thing, 1 by t minus s, t equals s plus 1 by t, so half log twice pi minus half log sigma square minus half sigma square t minus s, t is equal to s plus 1 to t, just like before. And then we just take the equation, which is yt minus phi naught minus I equals 1 to rho phi I yt minus I minus beta naught minus I equals 1 to rho beta I yt minus I omega t whole square, right? So these are the two equations within the main equation. So basically that is very simple log likelihood function, and it automatically estimates the d parameter as well, the log likelihood function here, or delay parameter. And where theta equals, these are the parameters, phi naught phi 1 beta naught beta rho, and we have lambda gamma c, the threshold, and sigma square are the unknown parameters. The log likelihood function is maximized with respect to theta using one of the iterative algorithms always discussed, probably Newton-Raphson. This algorithm is simplified by using the log likelihood using the maximum likelihood estimator sigma square, which is simply epsilon square divided by t minus s. So generally we end up having t, but this is root over epsilon square divided by t minus s if we are to estimate the parameter sigma hat. We are familiar with that, right? Instead of t, now we are dealing with t minus s because we are talking about backward propagation with the delay parameter. To concentrate out sigma square from log likelihood just before, as before, where epsilon is the residual. Okay, let's mention it as Vt because we have always studied as Vt, so it will be easier for us to remember. So structure residual for the case of unknown, for the case of delay, if it is unknown, a grid search is performed by estimating the model for values of d equals 1, 2, 3 and choosing that delay that maximizes the log likelihood function. Okay, so this grid search we have done before, line searching, researching we have done before. An alternative method to compute the MLE is to perform a grid search on both D and C. So this is also after the function, how you call the function in the system. So we're performing a grid search on both D and C, which we have studied also. So in case of unknown, we are doing a grid search for D or for D and C both. The advantage of this method is that for each choice of D and C, now omega is now an observable time series, so the MLE of the remaining parameters is computed by regressing y on its lags and the lags associated with omega t. So if you have omega t, what it tries to say is that after grid searching, if you have D and C and omega t, you can find the remaining parameters with simple linear regression without maximum likelihood estimation, and the parameters are the ones that has the lag and the lags that are associated with omega t, which means the two different regimes or two different, located in two different regimes. That is estimation, and that was quite easy. And then let's move on to discussing testing. A natural test of threshold model is to perform a test of linearity by seeing if the model reduces to the linear autoregressive model. So now we want to see testing if we want to test that if the data the model is linear or non-linear, if it is going back to linear autoregressive or not. So restriction happens here by restricting the omega t parameters out, which means we are trying to eliminate or restrict the second regime. A comparison is, between these equations suggests a natural test statistics to determine exactly that's what I said. The parameters in the second regime are 0 for all I, can be based on either Wald or LM principle. Very simple. So whether it's linear or non-linear, that is the question. The distribution of any test statistic that tests this hypothesis, however, is non-standard because the parameters gamma and C are not defined under the null hypothesis. This is not a standard test because, well, we are forgetting about gamma and C, and the conventional MLE theory is therefore not directly applicable. An alternative approach is to test gamma equals 0 as omega t becomes a constant, resulting in the threshold models reducing linear AR models. So because this test, however, direct test would be non-standard because we are not referring to gamma, the D and C. Okay, so C is the threshold which we have not defined, as well as the gamma, which is how quickly a model adjusts, or the speed of adjustment has not been defined. So we can set these to 0 because an adjustment is not required. And what we just talked about, whenever we have gamma equals 0, ultimately the threshold models converge to linear autoregressive models, or they converge to a single model. Well, we have only binaries representing the threshold model, which is the Setar model, right? And here we're talking about that if and setting gamma equals 0 and c is a constant, all the threshold models reduce to a linear model. Okay, so when we just talked about those in the threshold model, so maybe you are testing in terms of threshold models. However, in this case, it is the parameters c and beta I that are now not identified under the null hypothesis. In this particular case, under the null, we don't have c, so we are comparing 19.8 to 19.5. Just have a quick look. Yeah, 19.8 to 19.5. What is missing from here? We're talking about indeed omega t, and beta I is missing, as well as what? See, the threshold is also missing. So what we're saying here is that in this case, beta I under the null is not identified, as well as we haven't seen any use of parameter c. And the threshold, there are two possible ways to address this problem. Luukkonen, Saikkonen, and Terasvirta suggest focusing on local asymptotics at gamma equals 0. This approach, so setting gamma equals 0, this approach has the advantage of yielding a test statistics with a standard distribution under the null hypothesis. Alternatively, Hansen proposes a solution based on local asymptotics at beta equals 0. So first method talks to set gamma equals 0. The other method suggests to set beta equals 0, which yields a test statistic whose distribution must be approximated by bootstrapping. So method of bootstrapping now comes into play. This discussion that follows focuses on the first approach, so by setting gamma equals 0. So if z equals, that element of most importance in threshold models, gamma yt minus d minus c, so that under the null hypothesis gamma equals 0, and so z equals 0 for the L star weighting function omega t 1 by 1 minus exponential of minus zt. The first three derivatives of the L star weighting function with so the first three derivatives of the L star weighting function with respect to zt. So you see here now we are not only setting gamma equals 0, we are setting the whole element to 0. So the first three derivatives of the L star weighting function with respect to zt evaluated at z equals 0 are, so now we are deriving omega with respect to zt. We have 1 by 4 the second derivatives with zt, and we are focusing on L star. We are focusing on L star weighting function only, that equation, and second derivative and the third derivative is minus 1 by 8. Using these derivatives in a third order Taylor expansion around of omega zt around zt equals 0 gives you now third order Taylor expansion, right? So omega zt minus 0 whole square by 6 gives you something like this. This expansion has terms in well, the elements, so that the weighting function is approximated by the cube. Okay, so this expansion has terms to the power cube. So weighting function is now represented with delta. The elements are being represented with beta, gamma, yeah. So this is represented with the delta, and you see is approximated by the cube, because the final approximation is cube. The Taylor series approximation represents the local behavior of the function in the vicinity of gamma equals 0, and therefore provides a basis of a test for linearity. So using the Taylor series, maybe we can do a test here. So from 19.9 substituting back into the main equation, which was 19.5, we see first regime, psi equals 1 to rho yt minus I, yt minus I, yt minus d, yt minus I, yt minus yt square minus d, yt minus I, yt cube minus d, because it's a cubic equation. So we have this equation. The regression equation looks like this, because we have a cubic equation here, right? So third order, because it's a third order autoregressive equation. All right. So we did bootstrapping, and we did different we had to do bootstrapping. We are willing to take a different approach of Lukanen, and we focused out L star weighting function. We refer that as ZT, and evaluated ZT at 0, evaluated ZT at the 0 and took derivatives, the first 3 derivatives, and from there we expressed our derivatives in terms of a third order Taylor expansion. From this third order Taylor expansion, we have so up until now, in summary, whatever we discussed, it's pretty straightforward. Starting from estimation, we suggested that a maximum likelihood estimation can be done on the or a full information maximum likelihood estimation would give us the values of the parameters. However, in many cases, the maximum likelihood estimation might not give us the delay parameter. So except for the delay parameter, we might be able to find all other parameters. Now if we want to know the delay parameter, it might be good to do a grid search on the system instead of a maximum another form of maximum likelihood estimation. If we can, through grid search, we can suggest both D, delay, and C, which is the threshold. We can simply, we might not need a maximum likelihood estimation, because we can simply do regression of YT on the lag parameters in regime 1 and regime 2, because this will help us to estimate the grid search. The estimated parameter of D and C will help us to define omega t as an observable time series, and so we can just simply do a regular OLS. And then we moved in to talk about testing, hypothesis testing, and in the first perspective, it is very simple, whether you have linear or non-linear time series model, and you just restrict the equation, removing the second regime elements will leave you a general linear autoregressive parameter. So you restrict by removing all terms that is associated with omega t. However, there is a problem with this system. The problem is, if I can recall, non-standard. The problem is this system becomes non-standard because gamma and c. What was gamma? The speed of adjustment, and c, the threshold. These two are not defined, and we need to define them in the system for our restriction. So there are two methods for test statistics which uses bootstrapping, Lucanon method, and the other one is Hansen method. So basically now we look into the TAR models, threshold autoregressive models, and we want to set basically we want to see when these models become linear, when they converge, and to find these things what we do is very simply, for example, you take a logistic threshold autoregressive model, so star L star, you take that model, and what do you do here is very simple. You basically set the elements of importance yt minus d multiplied to gamma to be z, and you are setting testing this against 0, whether z is 0 or not. So the weighting function, the weighing function, is something that you know, and you basically take 3 derivatives for on the weighing function, and you use these derived weighing function into a third order Taylor expansion. And when you do the third order Taylor expansion, you end up with the third order of the element, which in terms which has all of these parameters, the first, second, and third order, so that the weighing function becomes cubic. All right, and that gives you the basis for test of linearity, because now you want to check if your gamma equals 0 or not. So the speed of adjustment is 0 or not, and that becomes the base for, so you check against gamma whether it is 0 or not on the equation, on the very regular, very general third order Taylor expansion, okay, which is simply pi naught I, pi 1, pi 2, pi 3, becoming the autoregressive parameters with the lags, and each time is a Taylor expansion, so up until cubic. So this is the third way to do. So first, in test of hypothesis, we did restrict all the parameters, but then we didn't restrict all the parameters. We learned a way to restrict only the speed of adjustment, and that is a better way. We tried to restrict the parameters to look like a threshold model. That is another way, you know. So if you're looking into threshold models, if we can convert that to an autoregressive model. So this is how we do testing. With the disturbance term, ut is a function of where the disturbance term is a function of vt, and the approximation error from truncating the Taylor series expansion with the delay parameter is known. Now the delay parameter is known. This regression equation forms the basis of LST linearity test. So this is the LST linearity test, Lucanon, Sykenoon, and Terrazavarte. So Now this time we have the delay parameter known. Under the null there is no interaction term. In the autoregressions are basically the pi's are 0 with j equals. So in LST now we just need to set pi's equals 0. Alternatively pi's will not be 0. So regress, what are the steps? Very simple. Regress y on lags to find the restricted residuals, and then regress, you find the restricted residuals, structural residuals, and you regress structural residuals on all the lag parameters that are also associated with the delay function, the Taylor series. You take all the parameters that are located in the Taylor series and you regress your residual against them, and then you just compute the statistics. LM equals TS square, where T is the sample size, R is the coefficient of determination from second stage regression, and LM is asymptotically distributed as chi-square with 3p degrees of freedom. Why 3p? Because you have 3 cubic Taylor series expansion in this case, okay, because you have three gammas. So star and LS star. Sampling properties of linearity test for a sample of size 300 and 100,000 replication. Null is beta equals 0, which gives the size of the test based on nominal size 5%. The alternative hypothesis is beta is greater than 0, which gives the size adjusted power of the test. So size of the test based on nominal size, size adjusted power of the test. These two are important, and we have 3 cube, so we do it 3 times. 0.51, 1.5, these are the speed of adjustments that we use, and also use estimated betas. So for our test, and pretty simple, isn't it? This is pretty simple. For now this should do. 3 other variants of a test based on equation 19.10, which was the equation 19.10. okay, the standard cubic linearity test regression. This is the regression equation. So for the equation 19.10 are obtained by imposing restrictions on the parameters of the higher order terms. So now you can set pi to equals, so we said that we can set all the pi parameters as 0, so we can do that. That's what it said. These alternative versions of the test may improve the power properties of the test. So we are talking about power properties as a non-linear system, okay. So basically when beta equals 0, we have size of the test based on nominal size 5%. When beta is greater than 0, size adjusted power of the test, okay. So it is when beta is greater than 0, you have size adjusted power of the test, something to memorize, and that is how it is related to this term. So power property, size adjusted power of the test, is more improved, or beta is greater than 0 property is more improved for lower order terms in the Taylor series expansions. So these, the Taylor series, so 19.9, the equation that we just mentioned, is sufficient to capture the non-linearities in our model. So this should be sufficient to capture the non-linearities, because you see, this is a non-linear model. Basically all the models here are non-linear, are sufficient. The lower order terms in the Taylor series expansion in 19.9 are sufficient to capture the non-linearities in the model. This may occur, for example, if the weighing function is of S-star type, a property which is developed in the exercises. So if you have a S-star situation, let's have a look into S-star. If you have a S-star situation, so S-star is based on power of the test, so exponential of this element. If you have a star situation, in that case 19.9, which doesn't have pi's but is represented in terms of gamma, is sufficient. Okay, this omega t is sufficient to test for linearity. So it captures non-linearity. It can be 0, it cannot be 0. So that is the thing in a nutshell. So quite interesting to test for a hypothesis in these different manners. So the steps again one more time is that first we find the residuals, then we regress residuals on all the nonlinear parameters, the nonlinear ones specifically and the lagged ones, and after that we compute TR square, LM equals TR square, using the regression, because when we regress these equations, omega t and gamma are estimated from that, right? And then we do impose the restrictions. We do the test again by imposing restrictions on pi's, and that helps us to find if our system of equation is linear or non-linear. Sampling properties of the LST linearity test. So there is a table that gave me finite sample performance of the linearity test based on a small Monte Carlo experiment. So we use simulated data, and from that we test for linearity using using that as a sample. The data generating process is identical to that used by LST and is given by equation where this is the first region, then you have the second region where omega t is 5, first region yt minus 1 minus c threshold is 0, and the L star 1 plus 1 divided by exponential of this term in which nu is IID with 0 mean and 5 variance, or 5 standard deviation. The size of the test is 4.36% given in the column headed beta equals 0, which is close to nominal size 5%. The size adjusted power function increases monotonically, so we have the size mentioned to us. So 5% and beta is greater than 0, so this is 5% and these are 4.5% results. What it suggests that this pattern, the power function increases monotonically as beta becomes more positive. This pattern holds for all values of gamma, although the power tends to be tapered off for larger values. So have a look. So this increases as beta increases, right? For all values of gamma, this is a property that is captured for size adjusted power of test. When beta is greater than 0, we have our betas increasing, beta becoming more positive. So basically that is what is the equation used here, sampling property of linearity test. In the case where the delay parameter is unknown, the regression equation includes the intermediate lags y square minus d when you don't have the delay parameter known to you. Assuming d equals p for simplicity, so instead of d we use p. Autoregressive parameter, the augmented regression equation is, well, this is actually d, don't make a mistake. So yt minus I by 2, this is the same equation as 19.10. I equals 1 to p, j equals 1 to p rows and columns, ij yt minus I yt minus j squared by rows and by columns, y2 minus a y2 minus j cube. So this is a cubic equation. A potential problem with this auxiliary regression, okay, so by rows and by columns whenever we are doing a loop, that is what it is trying to say. And it's a very simple equation setup, is that the presence of a large number of regressors may result in terms of the problem with this regression is that when there's a large number of regressors are available, this may result in a loss in power of the test statistic. So loss in power of the test statistic. One solution is to choose one of the variants of the test outlined earlier by excluding some of the higher order terms. So we're going to choose one variant and we're going to exclude one higher order term. For example, by setting, we might want to set this one equals 0 under the null. The test is now based on the restriction of the rest of the parameters equals 0. So the one of the higher orders we want to exclude to prevent loss in the power statistics. Again, when we have a lot of regressors, we might lose the power in the test statistics. So how do we take care of that situation? We just exclude some higher order term, such as we're going to exclude pi2 here, and just against these equals 0. With this version of the statistic has a chi-square distribution with p into p plus 1 by 2 plus p degrees of freedom. So this degrees of freedom is known to us. Again, p is d, delay function, nothing else, just for the simplicity of the presentation. P is represented as d, and this is exactly the same equation, but it is easier to form a loop from this equation. So there you have the threshold models beautifully discussed, and we have discussed its estimation techniques, we have discussed the hypothesis testing on these models beautifully. Now we're going to start talking about an application of nonlinear system of equation, most probably the most important application, artificial neural networks. And as you may know, that has given birth to a new generation of topics of employment and of computer power that is moving the world forward with a lot of promise. So a very important discussion begins from here. It's very important to take a hold on our concentration. Artificial neural networks provide a flexible framework in which to approximate nonlinear process. So it gives you flexibility. Power is flexibility in terms of nonlinear process approximations. In their simplest form, they represent a threshold time series model in which the weighing function is now referred to as a squasher. So the weighing function is simply a squasher. So again, let's go back to the weighing function that it is referring to specifically. Who is the squasher here? So all these weighing functions, star, S star, L star, theta, and E star, of which we found L star is quite important. So these threshold models are being used in artificial neural networks, and they are called squasher. This colorful choice of terminology stems from engineering, where ANNs were initially developed. Following Creedy and Martin, ANNs are presented in the econometric framework in terms of model specification, estimation, and testing. Further discussion is given in Kwan and White and Lee, White and Granger. These papers are important to check. Creedy, Kwan, White and Granger. So specification, consider the nonlinear time series model, where you have the first region, then you have, what does it look like? The one that comes after theta, which is A star, exponential, smooth threshold autoregressive model. which is delta naught, but here is additional elements are here, exponential of gamma naught. Is it gamma? I keep, oh, delta naught plus delta 1 yt minus 1 vt. So now the threshold models are squasher in INN, and this is what it looks like, where after beta we just bring in the S star model, where Vt is again an IID with 0 and sigma square disturbance term. This is a special case of the tar model with lag equals lag p equals 1. Okay, so 19.5 tar model. So this is a spatial representation. See, this is the same equation with now the S star is used. It's exactly the same equation here. So with lag p equals 1, the wing function given by the logistic function, the wing function is given by the logistic function 19.6. So 19.5 and 19.6. Oh, these are all the models, and this is the equation that we revise much later. Now weighting function is given in and given by the logistic function, right? That's all. In artificial neural network parlance, the nonlinear time series model is known as a hidden layer feed forward artificial neural network. Okay, very nicely stated all the time, again and again this comes up. Hidden layer feed forward network, but this is a logistic function. We should not, this is the S star logistic function with p equals 1. Is just one autoregressive one parameter, nothing else. The hidden layer refers to the term delta naught delta 1 yt minus 1 element, the mother element, because it provides for an additional linkage between yt and yt minus 1. So it gives you an additional linkage between yt and yt minus 1, which is region 2, that is nested within the logistic function. So beautiful, right? This is a regular logistic, this is a regular representation of a nonlinear equation. The whole 19.12, where we have seen this is region 2, well, this is region 1 previously, and but instead of that, we after beta we are just bringing in the S star and the logistic function, and with a little modification, because we start with an initial value, and we say that this element where we have delta naught is representing a linkage between yt and yt minus 1, but these are hidden in a logistic function. Feed forward indicates that the model uses information at time t minus 1 to make prediction of the process at time t. That's all. The artificial neural network, very simple. The artificial neural network component is given by the parameters delta naught and delta 1. So these are the NN component which are important. Well, the logistic function is represented as squasher, as this function dampens the impact of large movement. This is the squasher, the logistic function, or all the threshold models, as this function dampens the impact on large movements in the lag values. So this is a decomposition of the prediction of ANN into linear, dashed line, and non-linear. So a prediction of ANN is this solid line. Simply are we using yt-1 data to find yt, that is feed forward, and regular one is very simple to and important to remember. The nonlinear model is a feed forward artificial. The hidden layer component is because we are hiding the logistic function. We are basically hiding the linkage in a logistic function. Yt and yt-1 is linked through a parameter which is delta, and that is hidden in the logistic function. But that helps us to make prediction. So this is prediction, decomposition of the prediction of ANN into linear and non-linear components based on equation 19.12. After estimating, yes, based on the equation, parameter values are 5.4, beta 2, and we have the elements that are, giving you the connection between yt and yt-1, -2 and 2. -2, yeah. The logistic function is perhaps the most commonly used squasher, although other alternatives such as the cumulative normal distribution and hyperbolic tangent are also used. Basically, I have used hyperbolic tangent. I haven't ever used the logistic function, but I have used hyperbolic tangent function, which kind of reiterates the one located in Kalman filter. But yeah, that is also a function, and that actually helps prediction on yt to yt-1. That's all. So let's decompose an artificial neural network. Artificial neural network is decomposed decomposing the conditional mean of the NN in equation we talked about into linear and a non-linear component. Okay, so conditional mean is decomposed into linear and non-linear components. Linear is simplify yt-1, non-linear component is the other component, the logistic function. So the total is that. Beautiful. The non-linear prediction ranges from 0 to beta equals 2. Okay, because we are talking about p equals 1. So beta equals 2, because we need to predict one period forward. Since the parameter beta has the effect of stretching the unit interval domain of the logistic function. The parameter delta naught causes the nonlinear function to shift to the right, while the parameter delta 1 controls that steepness of the nonlinear function around its point of inflection. Very important. While both delta naught and delta 1 helps us to predict the next parameter or the next location, delta naught helps us to move the nonlinear line forward, while delta 1 actually gives you the steepness at a given point in time, whether that's a oscillation, is a magnification. So beautifully explained artificial neural network. The specification of the model is commonly referred to as an architecture. Other forms of architecture, that is model specification. Architectures are model specification, nothing else. Again, nothing else. We have been talking about specifications all along, and whether our engineer suggests this is an architecture, this is just a model specification. Consists of including additional lags. If you can include additional lags, additional logistic function, different types of nonlinear function, and additional variables. With these we change the predictability slightly. However, at all cases, the prediction function, basically the function that relates the change, which is the parameters which actually the known parameters causing the changes, the allowing the prediction, is located inside a hidden layer or a logistic function. You can simply change the logistic function, which changes the predictability of the system. For example, the following hidden layer fit for artificial neural network has 4 lags and 3 logistic function. This might be interesting. So terminology. Dependent variable is target, input yt-1, output predictor, y, squasher, logistic function. Oh, hidden layer, equation inside the squasher, neurons, the unknown parameters. All the unknown parameters theta are the neurons, bias, the parameter delta naught. This is essential, very important, how artificial neural networks are talked about and how we actually know them. We can easily explain them. Target is the result, input is the earlier lag, output is the predictor or the expected value of the result, squasher is the logistic function, hidden layer is the equation inside the squasher, neurons is all the unknown parameters, bias is the parameter delta naught, connection strings is the parameter delta 1. Training and learning is basically estimation. Fitness function is objective function used in estimation. Tolerance is convergence, objective function. Epochs is number of iterations. Basically number of iterations is the epochs. Learning rate is the line search parameter used in estimation. Momentum is the backstep parameter. Wow, line search we use in MLE is learning rate. Momentum is backstep parameter used in estimation. One more time, okay. Architecture and specification. Target is dependent variable is known as the target. Input is yt-1, output is predictor, logistic function is the squasher, hidden layer is the equation inside the squasher, inside the logistic function. Neurons is all the unknown parameters, nonlinear equation inside the logistic regression. Bias is the parameter delta naught, connection string is the parameter delta 1, objective function is the fitness function, tolerance is the convergence criteria when the models converge, number of iterations is known as epochs, learning rate is line search parameter, backstep parameter, momentum. So these are important artificial neural network terminology. Feed forward network has 4 lags and 3 logistic functions, with 2 of the logistic functions feeding into the third logistic function. So we have 2 of the logistic functions used to forecast the third logistic function. So you see, this is the first element. You have 4 parameters. What do we have? One more time, the question suggests we have 4 lags. So 4 lags and logistic functions. We have 3 logistic functions. Well, 2 are important because they are actually giving information to the third one. So this one is pushing forward, this one is the steepness, and using this we further determine another steepness where our omega, alright, where our omega or the nonlinear portion here, nonlinear determinant is is just this, the nonlinear equation, the component is just in loops. We can represent in loops instead of manually inputting them. This is the relationship I equals 1 to 4 for ji yt minus I. Why? Because these are feeding into the third logistic function. The first 2 are feeding to the third logistic function. I equals 1 to 4 j and I. Well, j0 I4 yt minus 4 up until yt minus 4. This will for j equals 1 and 2. So this is your exponential function. The econometric equivalence of other commonly adopted engineering terms are given. Beautifully we have seen that the unknown parameters are called nodes. Okay, neurons. All the parameters we estimate are neurons. The parameter delta naught is called the bias. The parameter delta naught is the bias, and it we know it, and it pushes the point of inflection of the logistic function away from 0, right? So this is the bias, as we know, and the connection strength, right? Number of iterations, we use I's, learning rate, momentum, convergence criteria. The parameter delta 1 is called the connection strength, since it controls the influence of yt-1 on the squasher, because it so delta 1 is actually the connection strength and hence the output. It is controls the output because it controls the influence of yt-1. Not only it controls the influence of yt-1 on the squasher, or influence of yt-1 on the equation, it gives you the output. So is the connection strength. One more time, okay? Whereas delta naught is pushing the function away from 0, delta 1 is connection strength, because it doesn't only control the influence of the lag variable in the equation, in the function, it also helps you to find yt from yt-1 and make one step ahead prediction. Okay, and that is the point of using ANN prediction. So let's do an estimation. For a sample of t equals 1 to t observations, the unknown parameters, which are the nodes, new rods of the NN is given in equation, can be estimated by MLE, assuming the structural error is 0 mean and sigma square variance in and the maximum lag length is 1. The conditional log likelihood function is, well, half sigma square t minus 1. We talked about t minus s before. This is t minus 1, y minus phi 1 minus beta omega t whole square, right? The whole thing is now omega t function and beta, whereas omega t is the logistic regression function, and we can use any of the iterative algorithms. In most application of ANNs, there is no explicit discussion of estimation issues, not necessary. Instead, the terminology refers to presenting the data to the neural networks and NN being trained to learn the unknown structure under the dynamic blah blah blah. This has something I have been learning all the time, causing so much confusion. You see, data to the neural network and the NN being trained, this is being estimated to learn the unknown structure underlying the dynamic process connecting the target to the inputs. Okay, so this reference is saying that, well, you are training the data that you don't know about the structure, the dynamic structure, but the dynamic structure is actually helping you. So yt-1 is helping you to find yt. You're basically doing nothing but estimating the parameters, and when you estimate the parameters, you automatically have the yt-1 yt, but the process is called learning process. Learning is based on a fitness function, which is an objective function, as well as additional controls for tolerance, okay, and a number of epochs. So generally what it means that we use an objective function, we always have done that, and we are giving a default tolerance. Okay, so whiles we have seen giving default tolerance, and sometimes we use for loops. So while loop and for loop, that's it. Number of epochs, that's all, nothing else here. So we can control with epochs or we can control with default tolerance. Table 19.3 has shown that the training and learning are just synonyms for estimation, and the fitness is simply the log likelihood function. Okay, learning arises because starting with some initial parameter values does not generally yield good outputs of the target. So when we are doing generating, we are saying this learning because starting from theta naught we don't get good prediction. As the algorithm is an iterative procedure, there is learning at the next step with the updated parameters yielding better predictors. Okay, this is something we have always done. What we have done always, we have started with the initial parameters, and whenever we took 100 extra observations, and whenever we estimated at the end, we removed, even in simulation, we removed the first 100 observations, because initial values do not give you a good predictor, but each time we move forward, the predicted values dependent gives good prediction in an iterative, in epochs. So there is learning. That is it. This is learning. The number of iterations, I mean, this has confused me, because I work in ANN in the beginning so much, to such a huge degree. I end up thinking this is a Kalman filter algorithm. This is Kalman filter, and Kalman filter algorithms converge here, but not necessarily it is that complicated as Kalman filter. It's just a nonlinear equation. The number of iterations required to achieve convergence is referred to as a number of epochs and convergence criteria. Very simple. All right, so that was estimation. Now let's talk about back propagation, something very important. So whatever we learned here is artificial neural networks. The terminologies that we always use, we use while and for loops all the time. We use the estimation of parameters. We see that an star similar to an star model, the logistic function is something similar to an star model, and the logistic function, the parameters inside the logistic function helps you to predict yt from yt minus 1. So that is prediction, nothing else, just like an autoregressive function, but it's a non-linear autoregressive function, that's all. The gradient algorithm for back propagation, the gradient algorithm that we have discussed up until now, is used to estimate the unknown parameters of an econometric model based on first and second derivatives. Do you remember? Yeah, we have done it so many times. Although these algorithms are well known and widely used in econometrics, they tend not to be widely adopted in. They are not very adopted in ANN. Instead, the so-called back propagation algorithm is most commonly used. Back propagation is something that we need to learn in, actually look into in Kalman filter algorithm. A representative iteration of this algorithm is given by theta k equals theta k minus 1 minus tau delta log theta by d theta, plus this is the back propagation for the residual k minus 1 to k minus 2. So theta k minus 1 by tau. So this is the backward propagation algorithm adopted from Kalman filters. And this back propagation is used also to find unknown parameters, not the gradient algorithm. Tau log theta divided by theta plus v theta k minus 1 theta k minus 2. Very important equation, where theta k is the parameter vector at iteration k, log theta is the log likelihood function at observation t. Okay, so the objective function or the log likelihood function, which is also known, our log objective function is also known as fitness function. V is the momentum. Momentum is convergence, right? Backstep parameter, the backstep parameter. Okay, so the momentum, V is the momentum, the back step parameter going backwards, k minus 1 minus k minus 2. Tau is the learning rate. What is tau? Learning rate. And learning rate is basically line search. So line search algorithm is used as line searching. Line searching is taking information matrix and using Hessian instead of gradient, if you can remember. So tau is the learning rate, and there is a V here, or what should I say, epsilon is the momentum. is the backstep parameter. The latter two parameters are used to aid convergence and correspond to line searching and backsteps respectively. Used to aid in convergence. This is used in convergence. Okay, line search up until convergence happens, and backstep. White and Kwon and White show that by choosing the learning parameter tau equals 1 by tk, 1 by t to the power k, where k is located between 0.5 to 1, theta k tau equals inverse of the time, well, tau equivalent to inverse of the time, t minus k, tau is line searching parameter, which is the default convergence criteria, and if we set it to 0.5 to 1, theta k almost surely converge to theta naught. So the parameters basically converge if we follow this equation. The most notable feature of the backpropagation algorithm are that it uses first derivative only, and that iterations correspond to scrolling through the first derivatives only is used. That is the most notable feature, and that its iteration correspond to scrolling through the sample, evaluating the log likelihood function at time t only, and not averaging over all t, as would be the case with standard gradient algorithm. The difference with a standard gradient algorithm and backward propagation is it uses the first derivation and it scrolls through the sample that evaluates the log likelihood function at time t only. Okay, so only one time is taken and only the first derivative is used. Much easier. This suggests that the backpropagation algorithm is computationally less efficient than the gradient algorithm that use all of the information in the data at each iteration, as well as additional information in the form of second derivative. Wow, a very strong statement, a strength of econometrics over engineering. Backpropagation is computationally less efficient than gradient algorithm that is using all the information in the data at each iteration, as well as additional information in the form of second derivatives. Because we are just taking the first derivative and we are not taking all the time periods for backpropagation, that is computationally less efficient. This calls for a different color. Wow, loved it. Well, something for the econometricians to be very proud of. All right. Now neural methods. So estimation is maximum likelihood. Just like before, there is no tweaks anywhere. Estimation can be also based on backward propagation, but backward propagation is nothing but a simplified gradient function. Yeah, that is besides maximum likelihood backward propagation. Then comes neural methods. For certain artificial neural networks, the number of unknown parameters can be extremely large. In fact, it is not uncommon in some applications for the number of neurones to exceed the number of observations. Okay, that is weird. Apart from the potential problem of imprecisions in the parameter estimates in trying to train, and okay, let's not talk about train, let's just talk about estimation. In trying to estimate an ANN with this number of unknown parameters, a gradient algorithm used to compute MLE can be expected to break down as a result of multicollinearity, causing the information matrix to be singular. So if you have more parameters than your observations, the gradient algorithm will break down, causing in multicollinearity, and information matrix will be singular, which would mean you cannot inverse the information matrix. And if you cannot inverse the information matrix, what will be the problem? you cannot basically estimate Hessians, or you cannot basically do a decomposition at all, right? Or find S. Even for the n and given by the equation, a gradient algorithm can still be expected to have problems in achieving convergence. One approach that is used in estimating NN is to choose values of the parameters from a random number generator. Monte Carlo simulation, we have done this before. The motivation for doing that, so basically instead of using any additional values, initial values, you just randomly generate initial values. The motivation for doing that is that its squashers with many neurons can begin to is that the parameters that are basically the autoregressive kind of parameters with so many unknown parameters can begin to mimic the brain, which has billions of neurons. Well, when you do a random generation, the system basically mimic brain with neurons, obviously because we have connection between yt and yt minus 1 through delta. That's all the bullshit here. One advantage of this approach is that ANN in equation, for example, now becomes linear. So now we have NN becoming linear because omega t is 0. Why is it becoming linear? Because we are randomly generating our initial parameters, and when we are randomly generating our initial parameters, our artificial neural network becomes linear. A very, very important statement. This is a different color. This should be a different color. You know, this should be, there should be a comment here. So when that's the problem, I'm just gonna pause it. Yeah, sorry. When we are randomly generating initial values with Monte Carlo simulation, what is happening to use initial values for the unknown parameters that we use for backward propagation, that is again used for backward propagation, the system becomes linear. The system becomes linear because you see the simulations generally use a uniform distribution mimicking the Gauss parameter, and generally simulations are symmetric. We want this because we want our information metrics to be non-singular, or we must have no multicollinearity in our system, and so we want symmetric parameters because we want symmetric simulated results, symmetric initial values to evade the singularity or multicollinearity, in another word, so that our matrix is invertible. Beautiful, right? Only in the case when you have more parameters. So you see, this becomes 0, a random draws at initial step, so this becomes the delta naught, the connection and bias becomes random draws at the initial step. The parameters phi and beta are then estimated by regressing y on yt minus 1, and this very simple regression. So we are randomly drawing deltas and we are estimating phi and beta by regressing yt on yt minus 1 and omega t. This procedure is repeated for another draw of delta naught and delta I, with phi and b once again estimated by the OLS after performing the algorithm n times. So we do a loop. We start with a random draw of delta naught and delta 1, and then we use a OLS. Then we do a random draw again, and then we use the OLS for n times. The parameter estimates are chosen as the values that will maximize the log likelihood function if it is expressed as a log likelihood function. So basically then this function is maximizing the log likelihood function. Up until it maximizes the log likelihood function, this process will continue, right? So that is a beautiful neural method estimation. When you have more parameters than your observations, then you have to kind of do random simulation. You'll continue to randomly draw values of delta naught and delta 1, and you'll continue to find estimations until your log likelihood function is maximized. This is a very simple process. Then comes testing. Now let's talk about testing an artificial neural network. Under the regularity conditions discussed earlier, a maximum likelihood estimator has an asymptotic normal distribution, as we know. 1 by t inverse of information matrix gives you the covariance matrix, as you can remember. In general, this asymptotic distribution can be used as the basis of undertaking tests on the parameters of ANN. However, as already observed in the case of the threshold time series class of models, care needs to be exercised when performing hypothesis tests when some of the parameters are not identified under the null. Similar to threshold models, we have seen that. The problem arises in testing for a hidden layer based on the hypothesis. Okay, because here delta naught and delta 1 are not identified under null. Restrictions of this form also constitute a natural test of nonlinearity, as the ANN reduces to a linear model under the null. The problem this time is delta naught and delta I are not identified, and if you restrict them, they become linear. Simple, just like threshold models. To circumvent the issue of some parameters not being identified under the null, one solution is to condition the model on values of delta naught and delta 1. So let's condition the model on the values of delta naught and delta 1, which are drawn randomly from a specified distribution following the neural method's approach to estimate ANNs. So neural method, as we saw, we simulate, randomly generate delta naught and delta 1, and basically we continue to do that until the use this estimated delta naught and delta 1 to regress and find unknown parameters until we maximize the log likelihood function. That is the neural method. So this time we need to condition the model delta naught and delta 1. Given values for these parameters, the first order condition for phi and beta under null are used to construct a LM test, similar to the approach adopted to test for nonlinearity in threshold time series model. So only the first order condition of phi and beta are used to test for the linearity in the threshold time series model. Why don't you just go up and see how we did testing in threshold time series model? Basically, so we took an equation and we set it against 0 when we are doing threshold time series model estimations. That's all, nothing else. This approach is suggested by Lee, Granger and White, who choose a rectangular distribution. We are talking about now this time we're talking about a rectangular distribution. Before that we talked about a cubic distribution. To draw the numbers, random numbers of delta naught and delta I, estimate the linear models. That steps are: estimate the linear model under null by regressing y1 yt minus 1 and extract the OLS for vt just like before. Choose delta naught and delta I randomly from a rectangular distribution in a range -2 to 2. Okay, randomly these numbers are chosen from a rectangular distribution. Construct the activation variable, the equation. So first let's do the first step and stay. Okay, before we did that vt, and we used that to find omega t. Regressed vt on yt minus 1 and omega t to extract the coefficient of determination from the regression. So let's go back one more time. What were the steps again for the previous testing technique? See, first we regressed, first we found yut and we regressed ut with all the parameters. That's all. This time it is the same too, but there is a few furthermore steps. More steps actually, little more, which is find vt just like before and use vt to find yt minus 1 and omega t. But before you do that, in between you randomly select delta naught and delta 1 from a rectangular distribution with a range, and you construct omega t with found the delta naught and delta 1 that you found. Then you compute lmtr square, where t is the sample size, and reject the null hypothesis. Lm is equal to chi-square. Very simple. The intuition behind this test is that any important nonlinearity in the data is excluded in the very first stage, will show up in the second stage regression, which is step 4. So everything you have excluded will show in the step 4 in the form of high value for the coefficient of determination. Okay, so that will cause a high value in R square. That's all. If there is nonlinearity, then R square value will be very high. If there is less linearity, reject null when this is greater than chi-square distribution. So if the value is less, then we cannot reject null and it becomes a linear model. So we are testing if the model is actually linear or non-linear, or parametric test, right? So we conclude artificial neural networks here. Moving from here, we'll move on to discuss bilinear time series models. Thank you.